In this lecture, we are going to see the conditional variance and then some computation formula for conditional variance. Okay, so the conditional expectation is the expectation with respect to the conditional probability density function or conditional probability mass function. The conditional variance is the variance with respect to the conditional probability density function or conditional probability mass function. Okay, so the conditional variance of x given y equals to y, that you can write as expectation of x minus x expectation of x given y whole square given y equals to y. Okay, and which can be again written as expectation of x square given y equals to y minus expectation of x given y equals to y whole square. So just like the previous case, that this is now a function of y again, and that sigma square y is basically nothing but variance of x given y. A variance of capital X given capital Y is denoted by sigma square capital Y, which is again a random variable. So I can talk about the expectation of this random variable or variance of this variable, those kind of thing I can talk about. Okay. Anyway, I hope that the conditional variance is fine, because you see that the condition in case of the variance, what was the variance? Variance is expectation of x given mu whole square, right? Expectation of x given mu whole square. So variance, we know that the variance, if I talk about the variance of x, this is basically expectation of x minus mu whole square. Mu is basically expectation of x, right? Now if I talk about the conditional variance, as I said, conditional variance is nothing but variance with respect to the conditional distribution. That means this is expectation of x minus mean. What mean will be there? Because it is the variance with respect to the conditional distribution, the mean will be the conditional. So that means it is nothing but expectation of x minus expectation of x given y whole square, y equals to y equals to y whole square. Now again the variance is the expectation, now this is a conditional expectation, so this expectation is also with respect to the conditional distribution. Okay, so this one will be replaced here by the conditional expectation, because the variance now I am computing with respect to the conditional distribution, so the conditional expectation needs to be used here. Then this expectation will also convert to the conditional. Okay, in this case it is an unconditional one, it is an unconditional one. In this case this one is conditional, similarly this one is also conditional. Okay, and now if you break this square term here, you will basically get that you will have this expression exactly. Okay, now as I already mentioned that this quantity is a random variable using the same thing that we have already talked about, because this one is a function of y. Say this is sigma square small y, then I am talking about sigma square capital Y, which is variance of x. And that variance of overall variance of y can be computed into two parts. The first part is basically expectation of the conditional variance, second part is the variance of conditional expectation. So it is very easy to remember, because first part is expectation then variance, and the second part is variance then expectation. So expectation of conditional variance and the variance of conditional expectation. Okay, and you can understand that inside variance is with respect to the conditional distribution, but this outside expectation is with respect to the distribution of y. Similarly, in this case, the inside expectation is with respect to the conditional distributions, and outside variance is with respect to the with respect to the marginal distribution of y. Proof is simple, and the technique is as we have used in many times. So we start with the variance. By definition, the variance is x minus mu whole square. Mu is basically the unconditional expectation, which obviously can be written in this form, and mu y is the conditional expectation. Okay, so now I introduce mu here, mu minus mu plus mu here, break the square term. I have this way. Now what I am going to do again is that I need to show that the cross product term is 0. And the cross product term is 0. You can show as we have seen in the as we have done in the previous theorem, the same technique we can use. You can show that the cross product term is 0. So I get that the variance of x is same as this part plus this part. Okay. So now talk about the first part. The first part is x minus mu y. Mu y is the conditional expectation. Okay. So I write this expectation as expectation of expectation with condition y. Now, what is this expectation? This conditional expectation part. This conditional expectation part is expectation of x minus the conditional expectation of y whole square given y, which is basically the variance of x given y. Okay, so the whole thing turns out to be expectation of variance of x given y. Now the next part is expectation of mu y, and then y, then mu is basically the expectation of x, which can be written as expectation of x given y. So this is expectation of mu y. So now you see this inside quantity. This inside quantity is a random variable set z here minus expectation of z. And then I have the square of this, and then outside I have expectation. So this whole expectation is nothing but variance of the random variable z. So this is basically the variance of the random variable z. So random variable z is basically mu y, and so I have this is basically variance of mu y, and mu y is basically expectation of x given y. So we have that variance of x can be written as expectation of conditional variance plus variance of conditional expectation. Okay, this formula is very handy that we will see in the next example. So next example start with that. Suppose I have a sequence of random variables x0, x1, x2, and so on so forth, and they are IID random variables with mean mu and finite variance sigma square. And suppose n is another random variable, binomial random variable with parameter np, and I assume that this n is independent of any xi here. Consider this random variable. Note that this random variable is very interesting one. See, still now we have talked about this kind of summation, but every time the summation is up to some finite value here, up to some fixed value here, fixed known value here, right? I equals to 1 to small n. Small n is something fixed before. But now instead of small n, I have a capital N. So this S random variable is the sum of random variables, sum of n number of capital N number of random variables. So sum of random number of random variables. Okay. So the S is the sum of random number of random variables. And suppose we want to talk about expectation of S and variance of S in this case. Okay, clear? The random variable is quite different from what we have talked about earlier. Is this okay with everyone? I hope that this is okay with everyone. That different in the sense that now the sum up to capital N, and capital N is a random variable. So this is a sum of random number of random variables. Okay, clear? Now, before going into the computation of expectation of x and variance of x, let us give some intuition where this kind of random variable are. So one of the example you can think of a car insurance company. In the car insurance, for the car insurance company, it is very important to know that for different customer, it is important to know that how much premium the car not premium, how much claim a particular customer is making. Okay, how much claim a particular customer is making, that is an important quantity. And you see that this quantity is exactly that. What is that? Suppose N, capital N is the number of accidents that is done by a particular customer. Okay, and Xi are the claims that he has made in the after the IS accident. So then N is also number of accident is a random quantity that one customer may have no accident, may have one accident, may have two accidents, so on and so forth. So N is a random variable, number of accident is a random variable. Similarly, the claim after each accident is also a random variable, because in each after each accident the customer may have different claims. Okay, so the total claim in a year is basically nothing but this quantity, where N is the number of accidents in a year. Okay, so for the insurance company, it is very important to know what is the average of claims, average of the amount claimed throughout the year, and what is the variance of average amount claimed throughout the year. So let us try to compute this. for our example, where exercise are IID with mean mu, variance sigma square assumed to be finite. Let us try to compute this thing. So I will proceed it using the conditional thing, because if I know the value of capital N, then finding out the expectation of S is very easy, because I can put, if I know that capital N equals to small n, I just put small n here and I do the computation very easy. Okay, so I do in this way, expectation of S given x equals to small n. I should change this small n because I have small n here. So maybe I need to change this one. I make this correct. So for the time being, take it small n, but this small n and this small n are different. Okay, you take this small n may be replaced by I, something like that I have to do. Okay, so expectation of S given n equals to small n, which is basically nothing but expectation of, instead of S, I write this expression and I got this one. Now notice that I have n here and I have n here. So these two things are not independent. But if I put small n here, because I know the capital N takes value small n, if I put small n here, then this part does not depend on capital N. And as we have assumed that capital N and exercise are independent, so this part and this part are independent, and I can get rid of the conditional part. So I have this quantity same as expectation of summation I equals to 1 to n xi, and here this n is fixed quantity, so this expectation I can find out very easily. It is nothing but n plus 1 times mu. Okay, so when capital N equals to small n is given to me, expectation of S is nothing but n plus 1 times mu. Okay, so now that means when I try to compute expectation of S, which is expectation of S given n, and expectation of S given n is nothing but this n need to be replaced by capital N. So I have this one. So this expectation of S given n is basically n plus 1 times mu. I need to take the expectation. This expectation can be taken very easily because this n is binomial one. So the expectation of this n is np, and I have this one. Okay, so the expectation of S is nothing but np plus 1 times mu. Okay. Now let us talk about the variance. So when I try to find out the variance, I need to find out what is the conditional variance. The conditional expectation we have already found. So conditional variance, again we will proceed in the same manner. It is the variance of summation xi, I runs from 0 to n, given n equals to n. I put the particular value of n here. Both the part are independent because no capital N in this part, only x's are there. So this n equals to n can be removed. And now I have a variance of summation of x's. X's are independent among themselves. So this variance of summation of independent variables, same as the summation of variance of the variables. Summation of variance of the random variables. So that was turns out to be n plus 1 times sigma square. So variance of S given n is capital N plus 1 sigma square. So plug in them here. Now I know a capital N has a not a binomial distribution. From there, the expectation is NP and the variance is NPQ. NP into 1 minus P. So just plug in them, you get. Okay, so using this formula, using the variance formula, the finding out the variance, and using the expectation formula, the finding out the expectation in this kind of scenario is quite simple. Okay, I stop here. Thank you for listening.